Good afternoon, everybody. You're in South Seas IJ. This next presentation is breaking kernel address space layout randomization with Intel TSX. Our presenter is Yeongjin Jang. I got a couple of quick announcements before we get started. There's a welcome reception in the business hall, which is in Bayside AB. That's down on the first floor. That's from 1730 to 1900. There's also the Black Hat Arsenal is on Palm Foyer on level 3. That's the one we're on. Back over by the escalators. A lot of neat stuff there. Definitely want to check that out. And also the Pony Awards tonight in Mandalay Bay BCD. That's on level 2. That's at 1830. So that's always a good time. You want to enjoy that. If you haven't already, please put your phone on vibrate or silent so that it doesn't interrupt the talk. And with that, I'll turn it over to Yeongjin.
Good afternoon. I'm Yeongjin from Georgia Tech. And today I will present our talk titled DRK, Breaking Kernel ASRL with Intel TSX. And this is a joint work with my colleague, Dr. Sangho Lee and Professor Taesoo Kim. Let's start with the easy one. What is kernel ASRL? So on the slide, there are two news articles, and one is for iOS, and the other is generally for Windows. And what they say is bypassing ASRL is required for the successful attack. Let's take an example on how kernel ASRL makes effective defense against the exploits. In Linux, on launching privilege escalation attack through the kernel exploit, the attacker might try to call two functions. One is prepare kernel create with 0 to prepare root credential, and the other one is called commit create, which is making current user as a root user. The code in the figure is actually extracted from the real kernel exploit in 2010 and 2013, and both of them calls those two functions in the exploits. But however, the attacker is required to know the exact address of those functions for the successful exploit. Previously, those addresses are fixed, and by accessing proc file system at KASLR, it'll be easily to be retrieved. However, in the recent Linux distributions such as Ubuntu, it is prohibited to access that as a non-root user. So if you access at that location proc KASLR with non-root user, what you get is just all 0. All the address values are masked as 0, so it is secret. And if kernel ASRL is enabled, the address of the function is changed per each boot. So, for example, on first boot, those functions are located at FFFF AA0A, and on the second boot, the addresses are completely changed, like it is located at BD0A something. Yeah. So, therefore, the attacker need to find a way to get the address value before actually launching the attack. And there is another example that shows kernel ASRL make kernel exploit harder. In 2015, in the last year, there was a privilege escalation attack in Mac OS X called T-Pound. And for the successful attack, the attacker exploited 3 different vulnerabilities. And of course, the first one is the information leak vulnerability, which discloses the layout of kernel memory to bypass the kernel ASRL as a first step. In fact, kernel ASRL is a statistical mitigation for memory corruption vulnerabilities such as buffer overflow or use after free. And the mechanism is very simple. It shuffles the address of the code and data per each time of boot or per each load of the module or drivers. And since it randomizes the location of the code and data, so the attacker need to figure out where the code is or where the data is to launch the successful attack. And it is very effective mitigation. For example, in Windows, there are over 8,000 locations the kernel can be located. So the attacker's success chance is less than like 1 over 8,000. As shown on those examples, the kernel ASRL introduces the additional bar to the exploits. So without kernel ASRL, attackers are only required to find a memory corruption vulnerability and then exploit it. But now, they first need to find an information leak vulnerability to get the address value correctly. Then they can success the exploits. In short, now the attackers are seeking for the information leak vulnerability to the successful memory corruption exploit. Because of its effectiveness, the modern operating systems have adopted kernel ASLR. It was Microsoft Windows which was the first to adopt kernel ASLR in 2007, starting from Windows Vista. And then both OS X and iOS adopted it in 2012, which make a jailbreak more harder. And finally is pushed into mainline Linux kernel starting from version 3.14 in 2014. However, in 2013, Hund et al. Presented a very interesting work called Practical Timing Side Channel Attack Against Kernel ASLR in Auckland. And the attack is a side channel attack caused by TLB cache in the processor. An important thing is that it is a hardware level attack, so no information leak vulnerability in the software is required to break kernel ASLR. So, which makes kernel ASLR ineffective. In their attack, they use TLB hit miss as a side channel. So let's learn about that, how the attack works by example. Yeah. So first, if we access a kernel address at the user space, what you get is, regardless of its mapping status, for an unmapped page, we get segmentation fault, which is caused by page fault at the processor because it is invalid address. And even if it is a mapped address, because we are in the ring 3, but the address privilege is in ring 0, so we get page fault. So it turns out as a segmentation fault at the user level. So as a user level, we cannot distinguish which one is different. Yeah, which one is what. But internally, the processor treats that fault differently. If it is a mapped address, then the reason for the fault is that it is just an invalid address. So to check that, the processor is required to walk through the page table, and then there's no page table entry, so it generates page fault. On the other hand, for the mapped address, the reason is different. There is a page table entry, but its privilege is ring 0, but we are in ring 3, so it's access violation. To check that, the processor is required to do the same thing with the unmapped page, go through the page table work, but different thing here is there is a page table entry at the end. Then the processor catch it first, then try to compare the privilege, then it generates page fault. So the different thing is that now it is cached into TLB. The caching here creates fast and slow path that can be exploited as a timing channel. For example, if a mapped address generated page fault, the processor translates the address and cache it to the TLB first. So on the second axis, it will be TLB hit, so mapped address get the page fault more quicker than the unmapped page. So in contrast, for the unmapped one, it must go through like a TLB miss and memory access through the page table work, then the processor can figure out it is page fault. So the difference in path, having 5 more memory accesses through the page table, creates a timing difference around 40 cycles internally in the CPU. And exploiting this timing channel can be done as follows. In the example code, we prepared a try except block, an exception handler in Microsoft Windows to catch the segmentation fault, which is a page fault from the CPU. And inside the try clause, we mark timestamp first, then intentionally generate page fault by accessing kernel address inside there. Then the processor will generate page fault, then operating system will handle this fault, then finally it will call back our exception handler So at the exception handler, we mark timestamp again. Then we can measure the timing between the before accessing the kernel address and then after the page fault happens. By using this method, Hund et al. Resulted that for a specific processor, if a page fault took less than certain threshold, like 4,050 cycles, then it will be a mapped address. So the figure on the right side is a graph from their paper, and it seems there's a tendency of lesser timing on the mapped pages on the bottom. Yeah. However, we can see that the channel is quite noisy. We can see lots of dots around the 4,050 cycles, so it is very hard to be clearly distinguished. Then why does this channel has much noise like that? And let me break down the timings about the current configuration. So to measure with the try-except clause, we measure the timing from the user to the processor, and there will be TLB hit-miss side channel, and then there will be operating system exception handling routine, and then it gets back to the user's exception handler. While we measure the cycles around 4,000 cycles, the most of time is consumed by operating system side. And the lengthy execution on the operating system part could suffer lots of noise because there could be like a scheduling interrupt or other exceptions, etc. So it could suffer lots of noise. And compared to the origin of the side channel, while TLB hit-miss just cause like a 40 cycles, this noise at the operating system is much more than that. So it makes the channel to be much noisy. So there is a research question we come up with. If we can eliminate the noise from the operating system, then the channel will be more stable and more accurate. So can you do that? So on the next, I will present an attack core called DRK. Comes from de-randomizing Kernel ASLR, which made a prior timing side channel attack to be more practical. So in summary, DRK overcomes the noise of the prior attack and has better speed, like 5 seconds in Windows and 0.1 second in Linux with 100% accuracy. And it's covered because there's no operating system handling routine involved. And its precision is much better. Like we can also detect executable or non-executable page, while the prior attack cannot do. And we make it like a very practical, so we apply the attack to all of the commodity operating system like Linux, Windows, and OS X. And the story of this attack begins in 2014. On surfing the web, we found a blog article written by a famous hacker, Rafael Wojciech, that says that Intel TSX can make this TLB side channel of kernel ASLR less noisy. Yeah. And in the article, it says with the TXX, the access to the mapped address returns fault in 172 cycle, while the mapped address returns in 200 cycle. So there's 28 cycles of the timing channel, but important thing is that their standard deviation is only 0 to 2, which means if it is depicted, there's a channel width like 28 cycles, but the noise is like 0 to 2 cycles, so the noise is very small. So it could be like can be clearly distinguishable like this. In contrast, using a try-except clause, it is measured like around 2,000 cycles, and channel width is around 20 cycle, but its standard deviation of the measuring time is around 35 to 57 cycles. And it looks like while the channel width is just 20 cycles, its standard deviation is much more than that, so it suffers noise. Then, what makes the timing channel stable in TSX? Before getting to the TSX directly, let's cover the background on the Intel TSX. TSX, Transactional Synchronization Extension, is a new instruction set that helps accessing data atomically without having traditional locks. And for the audience who might don't know about what is the traditional lock, let's cover that first. So in traditional lock, to create an atomic region, the user need to acquire the thread, acquire the lock. And this acquiring operation may be blocked if the other thread holds the same lock at the same time. Yeah. So thread will be waited until it gets the lock. And after that, if acquire is successful, then the atomic region can be executed. And if lock is successfully acquired, this atomic operation is guaranteed to be executed. And then to let the other thread use the same mutex, the thread need to release the lock after the atomic region has been finished. Good thing of this lock is that it is guaranteed to be executed for its atomic region. However, drawback of this approach is it is slow because a thread need to be blocked and wait for the other thread to release the lock, and it creates problem like deadlock if the programmer did not carefully use the lock and lock correctly. So TSX is introduced to resolve such drawback of the traditional locks. Its usage is very similar, but yeah, it's quite different. So calling xBegin is actually similar to like acquiring lock. But at this time, there's no lock at all. So it does not wait. Then it tries to execute atomic region. So it just try, but it could fail. If there's another thread working on the same data, or if there's another exception, it could fail. So it has an exception handler at the end. So if the atomic region successfully committed, then it lets through the thread runs. But if it failed, it let the programmer to handle that in different way. So in that case, programmer get back to guaranteed execution with the traditional lock, or they can try the TSX again after resolving the data thread races or something. And there are several reasons that TSX can fail. Of course, the definite reason is that if there's a thread races, it will fail. And in addition to that, if there's a cache eviction or interrupt, it will fail. And more importantly, it will fail if there's a page fault happens. And we are very interested in page fault because in the timing side channel attack, we are looking for that. And another important part of TSX abort is if an exception like page fault happens in the TSX region, the processor suppresses all the exception. It does not send the exception to the operating system. Instead, it directly calls the abort handler in the user level. So this makes the exception path to be differ with the try except. In case of try except, the processor generates exception and it goes to the operating system, then it gets back to the user code. However, with TSX, the processor directly calls the abort handler. So there will be no exception delivery to the operating system. It returns quicker and do not suffer noise from the operating system. And using TSX to catch this timing is very similar to using try except. So we can use following code to check the timing. So before invoking TSX region, we can get the timestamp by calling rdtscp, and then we try to access a kernel address inside of TSX region, which will be always fail. Then the processor will call the abort handler. So we measure the timing before getting into TSX region and at the abort handler to measure the timing for the page fault. And the timing breakdown will be like following. So previously, we measured the timing like 4,000 cycles, including operating system exception handling. But in TSX, there's no operating system involved in the path, So it'll be much faster. So what we measured is around 180 cycles, while the timing side channel is 40 cycles, and also there is no operating system noise at all. And with using this method, we try to measure the timings of page fault of mapped and unmapped kernel address. And what you've seen is like for having a read access to a kernel address, the mapped address always returns in fast in the CPU cycles. And in addition, we try to attempt to jump into the kernel address, which means execution access. It definitely failed because we have no privilege, but what we measured for the timing is that executable addresses always return faster than the non-executable one. And for the next, I will show you the live demo on how this attack works on the Linux. And let's get into terminal. Whoa. Excuse me. It's a problem with the internet connection, so yes. Maybe I can try again. Yeah, it works. First, let's check the system status. So try to do uname -a to check the Linux version. So it runs Linux 4.4.0 kernel. And in its boot argument, KASLR, the kernel ASLR is enabled. And for the processor information, it runs with the Intel Core i5 6300 HQ processor, which is Skylake, the latest one. And in the CPU ID, there's a flag RTM, which indicates that it is enabled with TSX. And let's measure the timing. So first, we will try to read on the unmapped address. And I just picked just an arbitrary address, but it is always a mapped one in Linux. And try to read on this address, returns like 190 or 188 cycles. And then let's measure the mapped address. So to get a ground truth information, we use a root permission to get the kernel symbol from string tab, which is read on the address. And measuring this mapped address returns like 166. So you can easily see that for a mapped address, it took like 166 to 170, while for the unmapped address, it always takes like a 188 or 190, so we can see that exact timing difference. And then next is trying to launch execution access to the address. For the unmapped one, it took like 178 cycles or 176 cycles. And for the mapped but non-executable address, it took same, like 176. But for the executable address, so I just get the address of commit create, which is a kernel function, and measuring the execution page fault on this returns like 142, 146. So we can easily distinguish executable pages from the others by measuring timing, like if it is 140 something, then it definitely executable pages. And we conducted this experiment on 4 different processors across 3 different architectures, Intel's Haswell, Broadwell, and Skylake. And from all of the processor, we can see that clear timing difference. So always mapped page returns fault faster than a mapped one. And on accessing executable and non-executable address, we can also see that executable address always returns faster than non-executable one. And this is a graph of what we get from attacking the Linux kernel module space. And we measure the timing per each page. And it shows that it clearly separates out mapped and unmapped page and executable and non-executable page. And there's a clusters, and between the clusters, we cannot even see any dots. It means its noise is very small, and we can easily distinguish page mappings by the timings. And let's compare this with prior attacks. The prior attack shows lots of noise in the threshold area, but DRK does not suffer that kind of noise. And we launched a DRK attack to the various operating systems. Since DRK is a hardware level attack, it is naturally operating system independent. So we target all popular operating systems like Linux, Windows, and OS X. And for the operating systems, we launched two types of the attack. So the first attack is that try to find the kernel and module area and try to measure the permission of each page. So what you do on the attack is first to find the kernel ASLR slide, then try to measure all the pages of the kernel, then move to the modules area and do the same thing. Then we will get the map like this. Like for address range, we can determine that it is unmapped, executable, or non-executable, which is what page table has. And then we will get the ground truth information extracted by kernel page table and try to compare to calculate the accuracy of the attack. And after having this kind of the page table information, then we will do a type 2 attack. It is detecting the module's exact locations. And an interesting observation is that on both Linux and Windows, a module and driver are always allocated with the fixed size of the sections for the sum of the sections in the binary. So if we can get the binary and take a look into their non-executable, executable sections, then we can easily create the size-based signatures. So for example, in the first entry, leap AHCI has a 4,000 size for the executable and 4,000 size for the non-executable area. So if some of the module has like a 4,000 on X, 4,000 on NX, then it will be leap AHCI. So we also run this kind of attack to figure out where the location of the kernel module. So for attacking Linux, we target the same processor I just showed the demo, the Core i5, and running Linux kernel 4.4. And let's see the full attack demo on the Linux. So the attack is really quick, so please be careful. So attack is finished, and let's take a look into the result. So what it first do is that try to measure the threshold for the mapped address and executable address. And to do that, at this time, we don't have any knowledge. We assume that we have no knowledge about the kernel. So we just use null page for the simulating unmapped one, and having a read-only page and try to do write access to generate page fault, simulate the mapped page. And for having threshold for the executable one, we map the non-executable page on the user space and try to jump it to measure the timing, and also jumps into the executable but invalid instructions to generate the page fault internally to measure the timing for executable pages. And then we try to scan all the kernel address to find the kernel ASLR slide, and finding that region just took like 7 milliseconds. It's very fast. And do the same thing on the module area. It took like 11 milliseconds. And then go through each page, like each 4 kilobyte page, to measure the permission of each page. And we measured like around over 6,000 pages, and it only takes 92 milliseconds, which is less than 0.1 seconds, to break kernel ASRL in the Linux. And then we try to grab the ground truth information from the page table and try to compare the permissions. And for the all pages, we achieved the 100% accuracy. So the results from DRK is actually exactly matched with the results from the page table. And for the type 2 attack, we successfully detected 38 unique size signature. Yeah, and then we can identify that the 38 modules on the module space. And for the details, let's take a look into the actual mappings. So on the left side, the result is generated by DRK, and on the right side, it is from the information is extracted from the kernel page table. And it is just a Vim diff, so if it is something is marked in red, that means it is different. So, and please focus on this address and the permission part. So I will move down. You cannot see any kind of red mark on the address or permissions. So DRK can get exact mappings and exact address information as same as page table through the attack. And another interesting point is that we can detect the address of the module correctly. And for some of the modules, like for this ACP iPad and memstick, their size signature is not unique. So we could find there are two or more, but at least we can reduce down the candidates into 2. Yeah. So we can successfully detect the exact location of the modules. So the attack in Linux, we achieved 100% accuracy for across 3 different processors, and it took around 0.1 or 0.6 seconds for probing over 6,000 pages. And for detecting modules, we can uniquely detect like 38 modules among the 105 modules by the size signature. And we also did attack on the Windows for the latest version of the Windows 10. And the result is that we could achieve 100% accuracy for the kernel and 100% accuracy for detecting mapped and unmapped for the driver's address space. But we cannot achieve 100% for the drivers. It was 99.28, close to the 100%. And the reason behind here is that in the Windows, drivers has some of the memory area that can be dynamically deallocated or change the permission. So at the time of the attack, we correctly measured the timing, but later it could be changed by the driver works something else. So, and in addition, TSX has inherent limitation that if the page is marked as an inactive, we cannot measure the timings. Yeah. So we missed some of them, but still it is over 99%. And for detecting modules, we could detect much more than Linux because size variance in the Windows is much more than Linux. So we could detect 97 drivers among the 141 drivers. And for OS 10, we launched it on the El Capitan, and we just did like a finding ASRL slide on the OS 10. And we do it for 10 times, and average speed is like 31 milliseconds, which will be very practical to be used in the kernel exploit. And another interesting point is that DRK also works on the cloud environment. Recently, Amazon EC2 launched a new instance called X1, which support Intel TSX. So we do the same attack on the Linux by having an instance with the Ubuntu 14.04, and the result is that it was same, like getting 100% accuracy, but a little bit more time. Yeah. So the summary of the result is like in the Linux, Windows, and OS 10, we all got 100% accuracy of the page mappings, and it is very fast to be applied to like a breaking kernel ASRL for the real exploits. Excuse me. Next is analysis. Let's figure out why this timing channel happens and where is the origin of the timing channel. The first part is that the analyzing mapped and unmapped address. So Hund et al. Previously hypothesized that the origin of this timing channel is TLB. To figure out that, the best way is take a look into the processor, but it is very hard. So in the Intel CPU, it is marked as an Intel confidential, so we cannot take a look into that. But although it is somewhat black box, we ran an experiment that indirectly let us know the internals of the processor. So we probed both mapped and unmapped page, and at the same for 1 million times, and at the same time we measured the performance counter of data TLB hit miss, and result is shown on the screen. And interesting thing is that DTLB miss happens only 84 times for the mapped one, while unmapped one has a 2 million DTLB miss. So it looks like DTLB is definitely the reason for the side channel. And following is a diagram that shows the side channel, how side channel works internally in the processor. On the first axis of the unmapped page, it will be TLB miss and go through the page table. Then it will generate page fault. And even for the second axis, there's no entry to be cached. So it goes through the page table again, get page fault. So it always goes to the page fault. So it is slow. And for a mapped address, path for mapped address differs on the second axis. For the first axis, it miss on TLB, goes through the page table, then cache TLB here, then generate page fault. So on the first, it took slow path. On the subsequent axis, now DTLB hits and generate page fault. So there's no page table walk on the second axis, so it returns faster. Yeah. And in summary, DTLB hit miss determines that whether the page table walk is required or not. So that generates a side channel. So it always faster on mapped address for the measuring the page fault. And next is the side channel for executable and non-executable address. And at this time, we measure the hit miss counter of the ITLB because this is we try to execute, so we measure the instruction TLB for 1 million time of probing. And the first point, take a look, is ITLB hits on the mapped page. So there's only 12 misses on 1 million prob. So ITLB actually hits. But the weird thing is that the timing for the mapped page is actually same with the unmapped one. So it does not take the fast path. Why? Yeah, it's quite weird. So we think that ITLB is not the origin of the side channel in the executable and non-executable addresses. And the second point to focus is there is not even TLB hit on accessing executable address. So TLB hit count is around 590 among the 1 million probes. So there will be so the TLB is not even accessed on accessing kernel address as an executable way. So we think that ITLB is not even involved in the fast path. Then what will be the reason? And we try to find several documents and informations on the internals of Intel architecture. And luckily, we found a patent that is registered by Intel Corporation in 2010 that could be a hint for this phenomena. For the instruction cache, there will be 2 caches in the processor. One is L1I cache, and it is virtually indexed and physically tagged, which means it requires address translation to retrieve the cache. So in the figure, there's a TLB and it's at the center. Yeah, so it requires TLB translations to access the cache. And another one is called decoded I cache, also known as micro-op cache. While L1 instruction cache just stores the opcode of x86 or AMD64 instructions, this micro-op cache stores decoded instructions, something like RISC-like instructions. And important thing is that it is virtually indexed, virtually tagged cache. So it does not require accessing to the TLB. Yeah. And I will describe how this creates timing side channel in the following. For the unmapped page, it will do the same thing, like ITLB miss, go to the page table work, page fault. So it always takes slow path, it is slow. And for the executable page, first, it miss on decoded I cache, miss on TLB, go through the page table, cache on ITLB, and also cached on the decoded I cache. Then fault. And on the subsequent access, now it hits on the decoded I cache, so it faults faster. Then let's take a look for the, since there's no TLB access, no page table walk, so it is on the fast path. And next is analyzing how the non-executable but mapped page works with this type of access. So it will miss on the decoded I cache, miss on the TLB first, then page fault, cache on the ITLB, then page fault on the first access. And on the second access, now miss on the decoded I cache, but hit on ITLB. But would the processor generate fault at here? If it is, it should manifest faster timing than the unmapped one. So it is not. And we can find the reason from the reason of this why it cannot return page fault at the TLB hit from cache coherence mechanism in TLB. In the Intel architecture, TLB is not a coherent cache. What it means is that there is no mechanism to synchronize the cache among the multiple cores in the processor. And let's take an example. Let's say there's a one core and it sets some address as a non-executable. And then, in the meantime, core 2 can set the same address as an executable. So in the page table, it was marked as executable, but there's no coherency. So no information will be delivered to the core 1, so core 1 do not update or invalidate their TLB entry. And next, when core 1 try to execute that address, it says, TLB says it is non-executable, but there is a possibility that core 2 has updated the page table. So in such case, core 1 is required to walk through the page table and identify that what is the correct permission, then determine the fault. So the correct path will be like following. On the subsequent access, TLB will hit, but it says it is non-executable. So the processor needs to go through the page table walk, then retrieve the entry, and it is still non-executable. Then finally, it will generate page fault. In summary, for the executable address, it hits on the decoded I cache, so it always gets the fast path. But for the non-executable page, even if ITLB got hit, it needs to go through the page table walk again, then it can get the page fault. And for the unmapped one, it always go to the page table walk to determine the fault. So for the slow path, they requires a page table, so they returns slower time than the executable address. And next is discussions of this attack. So the attack with TSX is not 100% noise-free. So there is some of the tweaks that make noise lesser than the noise lesser. So, and one point is that since we measure the clock cycles, so the dynamic frequency scaling, such as speed step and turbo boost, can change the timing of the side channel. And to the successful attack, we need to make that processor's frequency to be stable. And one easy way to achieve this is that just run a while loop. And with like 1 or 2 while loops, it makes the processor runs as a full speed, and we can get the stable clock as a max speed. In that case, we can easily get the timing correctly. And another thing that affects on the TSX is that some of the hardware interrupts, like a timer interrupts or I/O interrupt, can abort the TSX other than the page fault. If it happens, we could get some more timings, even if it is on the fast path. And to avoid that, what it can do is like theoretically, cache side channel works on 2 probes, but we can enlarge the number of the iterations, like having a multiple probe, like 100 times. It makes the attack more stable. And another thing is that benefits of DRK attack. So it has less noise, and also all the exceptions are suppressed, so operating system never sees the fault. So it is very hard to detect. And there is a possible way of detecting this attack, and as we did, like measuring the ITLB hit miss or DTLB hit miss, it could be a traces, or there's a TX abort counter in the performance counter would be the trace of this attack. But if the attacker slow down the attack speed, or like probing just 1,000 pages in a second or something, then it is really hard to distinguish from the normal execution. And next is about discussion about countermeasures. We thought about some of the potential countermeasures, and one direct thing is that to modify processors to not to cache TLB or decoded iCache if the privilege is not matched. But this is difficult to be realized because it requires hardware modifications, so it is very hard to deploy, to patch on the deployed processors. And another way is that like turning off the TSX to secure the system. But in the software manner, there's no way to turn off the TSX, neither from the MSR, the model-specific registers, nor from the BIOS setup. So it might be disabled through the microcode update. Intel actually did that for in the Haswell processor, there's a somewhat the bug in the implementation of the TSX. So Intel released the microcode update to update, but yeah, it's hard to be done in this case. And another way is that we rely on the very high resolution timer, like by 1 or 2 clocks. Yeah, and it is always suggested to that reduce the resolution of this timing, but nobody adopts it because there's lots of legitimate use of the high resolution timers. And for the software countermeasures, a possible way is like remove kernel page tables from the user space. Actually, OS 10 has adopted these options for the sake of security. But the problem of this approach is that it incurs like too much overhead, like 30%. On every time of the word switch, it requires context switch, so yeah, it is hard to be applied to the operating system. And another one is that doing more finer-grained randomization, not like a page level. It could be like the inside of the page or something, but it could be helpful, but it will be very hard to implement it because of the compatibility issues or other technical issues. And another easy one will be like inserting some of the fake page mappings, like some of the unmapped page. We can make it as a mapped one to fool the DRK attack. Yeah. And in conclusion, with Intel TSX, we can break kernel ASRL, a popular operating system, with 100% accuracy and within 0.1 seconds without having software vulnerability. And the timing side channel attack is by hardware in DTLB for mapped and unmapped, and decoded iCache for executable and non-executable addresses. So we think that current KASLR is not as secure as expected, so some more research is required to make it more secure. Yeah. Thank you. And for the next, I'm happy to answer any questions, so please come up. And if you have any questions,